Section 6.6, rank 1 matrices and structure tensors. Let's see the definition. A rank 1 matrix is a matrix with rank equal to 1. The rank is, by definition, the number of independent columns of a matrix. So a rank 1 matrix can be expressed as follows. For a specific column, the other columns are scalar multiples of the specific column. So we can prove the theorem quite easily. Every rank 1 matrix A, which is in n by n dimensions, can be written as an outer product. A is U V transpose for some U and V. You may consider U as a specific column, and V can be the collection of scalars. A is U V transpose, a rank 1 matrix, then is matrix 2 norm and Frobenius norm are the same as U vector norms times V vector norm. Okay, here we can prove it quite easily. A matrix 2 norm is by definition this term, the quotient with x non-zero, and vector 2 norm, and is maximized. It can be written in this way, and so that once A is replaced by UV transpose, and we reach at this one. Okay, if we consider this portion first, that is a scalar. It can go out with absolute sign, and the remaining part is U, so that is U vector 2 norm. Now, that one is a dot product, and we can use a formula, well-known formula, and V transpose X, which is same as now, in fact, this is a dot product. That is V 2 norm, X 2 norm, and cosine theta. Theta is the angle between V and X. Now we try to maximize this one. Then also we know this one, there is 1. So maximum of cosine theta is 1. So that maximum value of this one is V2 norm. That is this one. Okay. So we proved that for the Frobenius norm, you can use the identity, and then you can see it quite easily. Just to do it yourself. Now, for UMV, given in this way, you can form the outer product. That is a simple metric computation, so that you can do it quite easily. And also, its 2 norm must be product of norms of these vectors. Okay. In this definition, we'll try to expand the definition of induced matrix 2 norm. For matrix A, is induced 2 norm is defined in this way or that way. You already know that. But that quantity is the same as this one, maximizing that scalar. For A, x is multiplied, so it is a vector. Now y is now, along with y, you take a dot product, then this will be the scalar. Its absolute value will be maximized under the condition x and y having length 1. So this quantity and that one will be the same, but we'll approve it, but we'll use it. So it is an expansion of the definition. We'll use this one. We can prove this one quite easily by using the expansion. A transpose norm is the same as a norm. Okay. If we try to use that expansion, then we can use it in this way. This one is a scalar, so its transpose is given in this way, but this term and that original inside this parenthesis must be same. So their absolute values must be same. Now, if we try to maximize with xy having norm 1, this will become a norm. This will become a transpose norm. Okay, that's it here. But for some inequality, sometimes you can prove the inequality using 2 steps. One is one side is larger than or equal to the other side, and start with the other side, and that is larger than or equal to the opposite side. So eventually 2 must be the same. That is exactly the technique used in the proof. Okay, start with the left-hand side, A transpose A 2 norm. Okay, by using the expansion of definition, it can be written in this way. However, this one is the same as now A Y transpose, so that this one is a dot product between AY and AX, so that we can use this formula, okay, that one, so that dot product is this one, so that this dot product is bounded by the product of this one and that one, and cosine theta is 1. Okay, so dot product is bounded by norm over AY and norm over AX. Now, once this maximized, then this term will become a metric norm. Again, this one will become a metric norm. So it's a metric 2 norm squared. Okay. One side inequality is proved, and we have to start with the other side. Okay, this one, a 2 norm squared. Now, okay, let's go to definition. Okay, a 2 norm is maximum of AX metric 2 norm, and that means that for some vector z, that is same as this one, a z 2 norm with z norm is 1, because we are choosing this one is maximized for every possible x having length 1, but among them one vector z such that this maximum will be same as az vector norm. When it is happening, z must be a unit vector, right? Okay, we'll use the fact here. So a metric norm squared is same as a z vector norm squared, but this same as az transpose az. Now we expand in this way. Okay, already this one is non-negative, so that is same as that one. Now, rather than a determined vector, we may try to choose an x and y generally and try to maximize. Then this quantity must be larger than or equal to that one. Because we can choose z, x is z, y is z, then it's the same. But we can choose x and y generally, then this term can be larger than or equal to that. Now, this maximum, by definition, is a transpose A metric norm. So we proved the other side inequality. So they must be the same. Using this fact, you can prove this one quite easily. Try to do it yourself. It is given, but try to understand it. Okay, now we'll go to the second part of the section, structure tensor. The structure tensor is a metric derived from the gradient of function. Okay, so it is defined in this way. S of x, the structure tensor, is gradient of f and gradient f transpose. So it describes the distribution of the gradient of f in a neighborhood. And it is often used in image processing and computer vision. Let's consider a specific case. Now, let the function f be defined in two-dimensional space. So we consider here a structure tensor in two variables. F is f of x, y, so that gradient of f will be f sub x and f sub y. Its transpose will be a row vector, f sub x, f sub y. Now this metric product will result in this metric. Of course, this structure tensor is symmetric. Quite easily you can see that. If you take transpose, then it's the same as the original one. And that must be positive semi-definite. And that means eigenvalues of the metric is non-negative. You can see it quite easily. Now, here the two norm of the structure tensor, the metric, is same as earlier. We already know that. That is rank 1 metric, and two norm of the metric is this one vector norm times this vector norm, but they are the same, so that gradient f two norm squared. That must be the maximum eigenvalue of the metric. For symmetric matrices, the two norm is the same as maximum eigenvalue. So it's true. But determinant of S is 0 because it's a rank 1 metric. That means this is a non-zero eigenvalue, and the other eigenvalue must be 0. So we can summarize the properties here. Lambda 1, the larger eigenvalue, is this one, gradient of f squared, and the corresponding eigenvector is here, gradient of f. We can check it quite easily. Okay. S times gradient of f is same as now gradient of f and gradient of f transpose, and that is S and gradient of f. Now if we consider this portion first, then that becomes gradient of f norm squared, and then gradient of f. Okay, see here, metric or vector, scalar, the same vector, so that must be eigenvalue, and that is the eigenvector. Right? Okay, for 0 eigenvalue, you can easily see that that is the corresponding eigenvector. Okay. This one, special case, but this one is now representing the stack tensor for grayscale image. Grayscale image can be considered as a function of two variables. So once you are dealing with grayscale images, then this stack tensor will be used there. And its stack tensor is a rank 1 metric. Now we'll go to color image processing. Color image is a three-dimensional vector functions. R component, G component, red, green, blue, RGB components for each point. There is R function and there is a G function value and there is a B function value. So you may consider color image as three surfaces, RGB surfaces. So if you take gradient, then now for RGB x derivative and for RGB y derivative, because these three functions are defined on two-dimensional space, so that the independent variables are two, so the gradient will be now x derivative and y derivative for these three components. Okay, here the corresponding tensor must be gradient of I transpose. Okay, we write here there is gradient of I and there is gradient of I transpose. Now we make the product, then in this product this is vector, so that the only possible way of the product is dot product. So from these two we make a dot product. From this we make a dot product to get that one, and along with these two we get this one, and along with these two we get this one. Okay, so the structure tensor of color images is no longer a rank 1 metric, but yet it is a symmetric. Okay, this one there is same, so that is a symmetric. Now let's try to find the eigenvalues and eigenvectors. Okay, here we know that anyway it is made along with this gradient and gradient transpose, so that here is 2 norm is the same as this gradient squared, and it is also symmetric, so that it must be here the large eigenvalue of the metric. So we can conclude from this one, now gradient of the, in fact this is gradient magnitude of the color image, must be square root of now eigenvalue, the large eigenvalue. To find the explicit formula for the gradient or eigenvalue and eigenvector, let's write the metric in this form. I'm sorry. So that one is j sub xx, that's a j sub xy, and j sub xy, and this is j sub yy. Now let's try to find the eigenvalues of this metric. So by solving this characteristic equation Si minus lambda I and determinant equals 0, that is characteristic equation of the matrix. This is a quadratic equation for lambda, and by using the quadratic formula, we can find the larger eigenvalue in this way. Okay. Now, its corresponding eigenvector can be here now. In after finding lambda 1, we put here Si minus lambda 1, so that we have here lambda 1 along the diagonal minus lambda 1. And here, you may try to choose, from one row, try to choose now orthogonal to this row. Then that choice is basically, in fact, this one is chosen from the bottom row. Okay, so we choose this one for the first component, and now for the second component, we are choosing negation of that one. Then this vector, this row, dot product will be 0, so that one is orthogonal to this row, so that it can be, if it is non-zero, then it can be the corresponding eigenvector. Okay, and this eigenvector represents the H normal direction. Okay, the structured tensor can be implemented in this way. Okay. Now, for given color image, now that is gradient magnitude, and theta is angle of that normal vector, normal direction. Okay, let's see here. Okay, first, by using the Sobel derivative, we can get ux and uy. So it's x directional derivative and y-directional derivative. Of course, these are, each one is now m by n and 3-dimensional. And here, jxx is dot product, and ux in third direction. And jxy is ux uy dot product in, again, third direction. jyy is uy dot product in the third direction. So we computed this portion for each one, and then now to get the larger eigenvalue, we have to use this quadratic formula, and that is exactly this portion, and that, so that here we have larger eigenvalue, and square root of this larger eigenvalue is gradient magnitude. That is here, this one, this equation. Okay, so we found the gradient magnitude. Now, once E1 is found, then the matrix minus E1 identity, so that we have here now S minus lambda 1I, that is this one, and we may choose the corresponding eigenvector from the first row or second row. If you choose from first row, then now change the position, and for one, and opposite here sign. If you are choosing second row, then now change the position and change the sign for 1, then now the dot product will be 0. Either this one or that one will be the corresponding eigenvector. However, one of them can be 0. For example, ux. So it is now horizontally not changing, all is changing in y direction, then there's no horizontal change, then ux must be 0 at some point, then jxs must be 0 and jxy must be 0. So that now here, in one of them, one row or the other one must be 0, which means that either this one or that one must be 0. So to avoid taking 0 vector, we have to choose the larger one in length, pointwise. In order to do that, now we start with this one as 1, 1, named it, and then here take absolute value and also take absolute value. So we are comparing these two. So they try to choose the larger one. Index is found. So by using this index, we try to get linear combination and along with this one, that one, so that pointwise, if this one is larger than that one in absolute value, then this one is chosen. If this is larger, then that must be chosen. The reason we can do this way is that after subtraction of lambda 1, these two vectors, and top one, bottom one, is dependent. One row is multiple of the other one. So that by comparing magnitude of this one, that one, we try to choose larger one pointwise. That is exactly this scheme. And then by using these two, and we can find angle by using tan 2, so that theta will save the angle of the edge normal direction. Okay. It is explained in this remark. So to avoid 0 and 0 vector, you need that. If you try to take only one, either this one or that one, then occasionally the eigenvector must be 0, so that your angle computation will be erroneous. Be careful. Here you have to do this one. Now, solvable derivative is a kind of a derivative, averaged derivative. And for example, with this kernel, now we are using convolutional operator along with this kernel. That is, now top is 1 to 1, center is 0, 0, 0, and this one is minus 2, minus 1. That means now it's vertical direction. It's trying to get the average, the derivative. Okay. Here a little bit complicated. The reason is in MATLAB, the built-in convolution operator has a little bit problem around edges. You have to take care of edge values. The reason is the default computation is done along with expanding outside the image values 0. So along with the 0 value outside, try to get here the slope, so that if you are not paying attention, then along the boundary you will have some meaningless values. So deal with the boundary value. It is made a little bit complicated. However, basically you can do it. This computation along with here some averaged Sobel operator. Okay. Now let's see one application of the structured tensor. We have original color image here, and that is gray image. Now, once you are using structured tensor, then along the edge, you can see edge direction quite nicely. So output of the structured tensor is making this plot quite nice. And during the competition, now it's a little bit averaged so that in this area, there's no observable the direction, which means that only along the boundary it made really good edge detection. Once it is transformed into grayscale, then by using the grayscale gradient, you can easily get the gradient and gradient direction. Then, as you can see here, for this area, the gradient is okay, but later on, the gradient is, the magnitude is becoming smaller, 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 so they disappear. And also, there are many noise components here. So by using structured tensor with averaged computation of Sobel gradient, you can get edge detection much better. So rather than transform it to grayscale and then try to use the grayscale gradient. And one of your exercise problem is asking you to use the structured tensor. I hope you enjoy it. Thank you.